Okay, so we are going to start our third lecture in Verilog, modeling and Testbench in Verilog. Again, we are covering the several topics in Verilog language. This is right here our main skeleton, the main skeleton of the language of Verilog. We will focus on some of the assign statement right here. We're going to focus also on the always and initial block and the type of procedural blocking statements and procedural non-blocking statements. Okay, so assign, okay, which is typically data flow statements, and the always and initial blocks, which can contain blocking statement, procedural blocking statements, like here, done here, or procedural non-blocking statement, like here. Okay, so all of this relates to how we can model the hardware. Now, it's important to remind ourselves that in Verilog, we can do structural modeling where we instantiate components and gates, data flow where we use the continuous assign statement, and behavioral model where we can use the procedural assignment in the always block. Remember, we talk about always block and initial block. The initial is typically used to initialize the test bench and the hardware. So it is not typically used to model actual hardware. So either we have the always block with a procedural assignment or the assign with continuous assignment. Now, so these are the typical three, the structural where we instantiate the gates and blocks, the behavioral where we have the always and initial blocks with the behavior procedure, or the data flow where we use the assignment statement. Now, so here is typically a piece of hardware here, two gates, an OR gate, and an inverter. And we desire to, typically we desire to, let me just move this window out of my way here. Just a small question. Is my voice clear? Is my voice clear? Is it okay, Masmoor? Okay, all right. Just continuing. Okay, so in the modeling here we have a gate, an OR gate, an inverter. So to model this in a structural way, okay. So if I may use my pen here. So this is the structural way of doing it, and we said these are just instantiation of a gates. So this is an OR gate, okay, and this is the inverter right here. Okay, I instantiate the inverter, and the inverter we use the keyword not, which means inverter, and here the keyword or. Keyword means already the Verilog language understand that this is an OR gate. Okay, and we do the connectivity as we have learned in the previous class. Okay, so this is the structural, which is instantiation of gates. I can model this in a different way, which is a data flow way, where I can use assignment. And now notice that here assign Q. Q is what? It is the NOR gate. So notice from the previous class, this is a NOR gate of A and B. Understand one thing, that Q here must be of type wire, and by default any output is a wire. So you cannot have Q as a register. You cannot. Okay, so it must be a wire. That's the output of an assign statement. Or I could do this in a procedural way using an always block, and we will understand later on what an always block. So an always block, and here Q, the output inside an always block has be always to be of type register. Okay, it has to be of type register. So Q here defined as a register, and it is equal to the inversion of the ORing of A and B. That's an OR gate. Okay, so three ways of modeling the same hardware. So the question is, why would you have a three ways? And the simple answer is, well, this is a very strong flexibility offered by the language, because sometimes you want to model things in a structural way. Sometimes you want to model things in a behavior way. So that's a very powerful flexibility by Verilog. And any hardware description language, by the way, would offer the same thing. Verilog does, VHDL does as well. Okay, so now let's talk about the assignment, the blocking versus non-blocking. Let's go about, with the skeleton here. So we said here in our skeleton, right? We can have always block, which is here, right? And I have an always block, which is here, right? What is the difference between the two? Well, this block here use a blocking assignment, right? And this block use non-blocking. There is a typo, by the way. This is a typo. Okay, this is a blocking assignment. Okay, and this block he use non-blocking assignment. So let's make the difference between these two type of assignments. So we come over here and say that here is the syntax of a blocking assignment. Watch, a blocking assignment has this equal sign. But if I have this equal sign with less than, this is called non-blocking assignment. What's the difference? The difference when we execute, by the way, in both cases, A and B, right, must be of type registers. Okay, so that's why we see A and B are registers. So they are, because they are assigned to them inside always block, and anything you assign to it inside an always block must be of a type register. Okay, so what is now the difference between the two? The non-blocking assignment are executed sequentially. So first we execute this, right? So we evaluate this. Then we move to the next assignment statement. So in this case, we have an initial block, and this initial gives an initial values for A and B. So B equals 0 and A equals 4. In this case, A will be B plus 2B, which is a 0 here, right? And therefore, A equals 2 here, right? And now, as we show here, right? And then next we evaluate B. What's the new value of A? It is 2, right? So A is 2 times 3, so B equals 6. So that's why B equals 6, and this is evaluated right here. So the blocking assignments means that we execute statements inside the always block sequentially. We finish a statement, update the values of the variables, and then we go to the next statement. Now, let's go to the non-blocking here. The non-blocking, all the statements are executed in parallel. The order is not important because they are executed in one time shot. So how can we do that? Well, when we get into the an always block here, what we do, we register the initial values of A and B. So what's the initial value of A and B? Well, for A, it is 4. For B, it is 0. These are the values that will be used in the right-hand side of all the statements in the always block, right? So B is 0 plus 2, right? So this A equals 2. Now, A is what? A is 2? No. A will be, A will be, let's change the color here. A will be the 4, okay? So A will be 4 times 3, which is equals to 12. But why choose 4 here? Because we capture all the initial values when we get into always block, right? Because we do not execute statements sequentially, rather we execute them at once. That's why we capture the initial values and it will be used on the right-hand side of all the equations and the assignments. So you can see here how B here is different than B here. Okay, all right, because this is blocking and this is non-blocking. All are executed in parallel. Now, blocking assignment, if you change the order of the statements, you change the logic typically. Non-blocking statements, if you change the order of the statements, you do not change the output. Okay. All right. So this is the non-blocking versus blocking statements. Now, so obviously you can see that here in the blocking versus non-blocking here. Okay, what's the syntax, right? We can use them in always and initial blocks, always and initial blocks. Okay, this is an example of them. Okay, this is an example, right? And typically the variables that you assign to them must be registers. So here in the examples, both A and B are of type register, Okay. All right. So this is pretty much the now what we have an example here of half adder. Okay. So we can design this half adder, right, using a structural design where I just instantiate the gates, right, and do the connectivity. Now I can do the same thing with a data flow. The data flow is using what? Assign statement. And we say that the assign statement do not live inside always or initial. They stand out. And this is the syntax. Assign this variable S or C must be either a wire or an output. In this case, they are output. And by default, all the outputs are wires. I can model them this way. I can model them this way. Both are correct way of modeling. And both are data flow modeling because we are using assign statement. Okay. So this is one way to model it. Now, what I could do is for the assign, okay? So now watch what we have explained. We have explained the blocking, non-blocking, and the assignment statement. Assignment statement differs by using the keyword assign, okay? They are not inside always block or initial block. I have seen this repeatedly. Many students, they try to use them inside always or initial blocks, and that's a mistake, okay? Now, here is a way of concatenating Q1 and Q0 and giving their values. So this one will go to this here, and this one will go to this. So you basically you concatenate expressions. Okay. Right. Now, let's do the same thing in terms of half adder, but now we want to use a procedural modeling. We'll use a blocking statement assignment. Okay, so this half adder, we will model it with an always block. We'll use blocking assignment. Okay, so this is S, and this is a sum, and this is the carry. But watch, what's the type of the sum and the carry? Registers. They have to be registers. The sum and the carry, they have to be registers. Why? Because we are assigning them inside always block. Okay. Now, here's a full adder that we constructed from two half adders, right? We can do the modeling using data path. Okay, data path, which means a assigned statement. So the output here sum, I can say that the sum is the exclusive OR of the three inputs, and the C out is this equation, which you can pick up from your previous courses in electronics. So we are just modeling using what? Using assign statement. I can do that modeling instead of writing the logic equations. I can use the addition, right? Because the sum and the out and C out, they are equal to x plus y plus z. Both are correct modeling. But the difference here you are using the gates, the XOR, the AND, the OR, and here you are describing the function, which is the addition. Valid modeling in both cases. Okay. So the assign statement basically, you are assigning a type of wire or an output. Okay, so these are the types that you can assign to, and the rest here they can be variables, they can be nets, they can be functional calls, etc. Now, one thing here so far, when we instantiated, uh, let's say this comes in the structural modeling, when we instantiated the blocks, we pass these inputs, right? So if you look at, for example, here, let's see where we have. Um, we are modeling this full adder. Let me just have a okay, so here we are modeling for this full adder, right? Using this half adder. We'll use it here and we will use it here. This is the description of the half adder. Okay, so the half adder uh, right here. Mhm. I'm just looking here. Unfortunately, there is a little bit here. This should be X and Y. Okay, so that we are matching what is being described here in the ports. Okay, that's a typo again. Okay, so now we need to model this full adder. Okay, so now what I do, I instantiate two half adders, and I need somewhere here an OR gate, and I instantiate this OR gate right here. Notice these are the connectivity for the pins for, okay. Now, when ports are many and it's very easy to make a mistake between S and S1 and C1. So this obviously signal S1 is connected to this S, and C1 is connected to C, and X is connected to X, and Y is connected to Y. And the other one, the sum, is connected to the S, and the C2 is connected to the C, and the S1 is connected to the X, and the Z is connected to the Y. Okay, that's the connectivity of these two. This is a half adder and a half adder, and they correspond to this half adder and to this half adder. But it when we are relying on passing these signals to connect to the same order, this is not appropriate if you have large designs. So what people do, they connect based on position. So based on based on name matching. So right here, instead of relying that I'm gonna send S1 to S, no, I write something like this. Port S, which is this one here, okay, will get signal S1, okay, which is this one here. Okay, so I'm saying that this port S will get signal S1. And here I'm saying port C will get signal C2. So this port C that here will get this signal. So I'm forcing this passing of signals. I'm not relying on the order, because in the order we make mistakes. And so, for example, right here, I'm saying that port S, which is this one here, right? I'm passing to it signal sum, okay, which is this one here. Port C, C2. So this is port C, C2. Port X, right? Okay. I'm passing S1. So this is S1. So the port X here right? I'm passing to it signal S1, right? And port Y, I'm passing Z. So this is port Y, which is this one here. This is port Y. I'm passing this Z signal. Okay. So this is called name-based matching of the ports. And typically people that recommend this way do not rely on the order of the pins. Okay, here's an instantiation of an arbiter using name-based matching. So another example. Okay, one thing we do typically in Verilog simulations is to build test benches, and test bench is what? So now you have finished your design, whatever your design is. We call it design under test. This could be a multiplier, it could be a compression machine, it could be a neural network, whatever you want. Now we need to test it. So what we do, we build a program here. We called it a test bench, right? And this program does what? It will generate inputs that goes to your device and will sample the output of this device and make sure that the output is correct. This program that does that is called the test bench. Okay, and it's typically, um, while it's very small and simple for your assignments, but typically is a huge program. And really in modern design teams, more than half of the team will be doing testing for the design, because the cost of having an error or a bug in the design is very, very expensive, especially in hardware. You see, a bug in software, you can always release a patch or a fix. But in hardware, if you have a bug, you really need to throw the chip away, and with it, you will be throwing millions and millions of dollars of investment. So having a design is which has minimal number of bugs, because you will never ever flush out the bugs. If having a design with minimal number of bugs is a great challenge for design teams in companies like Intel, AMD, Qualcomm, etc. Okay, now, so test bench, this is a typical test bench for your assignment. Typically, you have to instantiate the design. This is the design under test dot. We call it the dot. All right. And typically, you will have an initial block, right, where you assign values for the inputs. And you have a delays here. So you say here, for example, initially I'll have X and Y and Z equals zeros, then wait for 10 simulation times, and then change the value of Z to 1. So X will be still 0, Y 0, Z 1. So you can see in the simulation here, okay, this is your first pattern. All right. After 10 ticks, this is your second pattern, because you really just change Z. Okay. And you can go over this, etc., etc. These are your. So what you are doing is basically you are providing this stimulus. You are changing the input values, and then you are observing the output to make sure your design is correct. And these are the output that are coming from the design. Okay. I'm going to check them, make sure that my design had the right sum and the right. This is the job of what? Of the test bench, right? Now, for a full adder with 3 inputs and 2 output, you can inspect things visually, and you can have what we call direct tests, which means or comprehensive tests. But when you have a design where you have many signals, many control signals, you really cannot have exhaustive testing, and you cannot check the output that are coming from the dot with visual inspection, right? So you have really to build these sophisticated really programs here, which we call the test bench, that will generate the stimulus automatically, and check the result of the stimulus automatically as well for you. Okay, because you cannot. I mean, imagine you have about 2 billion or 10 billion tests, right? So can you inspect this visually? Of course not. Okay, so you need to create these test benches, right, which is really sophisticated program that generates stimulus input to the design and check the output of your design. Okay, so this is one part here of my lecture completed. So I'm gonna stop the recording now. Okay,